All right, Algebra 1, welcome back. We recently just talked about how to graph exponential functions and how to look at the pattern of exponential functions with their y-intercept and their rate of change in that formula y equals a times b raised to the power of x. So we were fiddling with that a little bit yesterday and on Monday as well with our marble sliders and stuff like that. So today we're going to look at exponential functions again, but we're going to be talking about writing an exponential function that represents a pattern or represents a scenario or a table. So we're going to learn how can we create the exponential function from the table and sort of write the rule for that function. So we know every exponential function has this form, y equals a times b to the x, where a is the y-intercept, I lost my E. And then B is the rate of change, the number you're multiplying by. X being your input, Y being your output. Sometimes we have a number that's being subtracted from the end of the function. Sometimes we have a number that's being subtracted from our X. We saw that a little bit more in the marble sliders, but we won't worry about that at the moment yet. But we know our function has to be this. So essentially, we need to figure out what is our y-intercept and what is our rate. And once we have both those pieces of information, then we should be able to create our exponential function. So looking at this table, I have -1, 1.25, 0, 5, 120, and 280. So first thing I need to think of is, what is my y-intercept? Well, I know the y-intercept always occurs when our x is 0. So my y-intercept in this case is 5. So my function is going to start off with y equaling 5. And now I need to think, okay, what is my rate, that b, that needs to go in for my rate? So something we can always do in order to find the rate is we can look at what are we multiplying by every time? And you might be able to see this pretty easily. You might be able to see, 5 to 20 to 80, that's always just multiplying by 4. But if you can't notice that, if you're not really good at just seeing the rate or that pattern as quickly, another trick you can do that will always work is take one y value, for example, 20, and divide it by its previous y value. So take 20 divided by the previous y value, the one that comes right before it. So 1 previous is 0. And we can divide these. 20 divided by 5 is going to give you 4. So that will always give you your rate. So I know 4 is my rate. So my function is y equals 5 times 4 raised to the x. And that's all I need to do in order to create my exponential function. Let's look at the second one. All right, so once again, I know it's going to be y equals my y-intercept. Well, I know y-intercept occurs when x is 0, which in this case is 3. So y equals 3 times my rate. In order to find my rate, I just take one number divided by the previous. So I'm going to take 18 divided by 3. One term divided by the previous term. 18 divided by 3, 6. So I know my rate is 6. So y equals 3 times 6 raised to the power of x. And that is my exponential function for my second table. And that's really all the trick there is for making an exponential function from a table. Once again, it gets a little bit harder if we add on the c at the end, that like minus c, or if there's a number next to the x, but we won't worry about that just yet. Let's look at two others of these. Once again, same strategy, same thought process. All right, so I need to think, okay, what is my y-intercept? X is 0, so y is 16. So it's going to be y equals 16. Then I just need to find my rate. Well, what is my rate that I'm working with? I just need to take two terms and divide them. So I'm going to take 4 divided by 16. 4 divided by 16. Well, 4 divided by 16 doesn't divide into a whole number. It's going to give me a fraction. But I can't simplify this. 4 over 16 is going to simplify. These are both divisible by 4, so this is 1/4. So 1/4 is my rate. So this is y equals 16 times 1/4 raised to the x. Easy enough. All right, jumping to this next one. My y-intercept isn't till down here, 0, 10. So I know it's going to be y equals 10 times my rate raised to the power of x. Then I need to just figure out what is my rate. So let's see, take two terms and divide them. So 50 divided by 250. Once again, this gives me a fraction. It's not giving me a whole number because 250 is larger. But both these numbers are divisible by 50. 50 divided by 50 is 1. 250 divided by 50 is 5. So my rate is 1/5. So 10 times 1/5 raised to the x. Once again, when we see that it's a fraction, we know it's going to be an exponential decay. We are decreasing every time because our b is less than 0. That rate when that rate is less than 1, in between -1 and +1, we know we're going to be decaying. We're getting closer and closer towards that x-intercept. Our numbers are getting shorter and shorter, closer and closer towards 0 every time. But when that number is greater than 1 or greater than negative or less than -1, it's going to get closer and closer either towards positive infinity, we're going to shoot up rapidly, or we're going to get closer and closer toward negative infinity. We're going to shoot down rapidly. Those are the two patterns we noticed previously. All right, fill in the blanks to create an exponential function that goes between the points A and B and the points C and D. So we're kind of like doing a slalom that you see in like the Olympics. We need to pass between C and D and between A and B. So we essentially need a function that looks like this. Some sort of function that has that curved pattern on it. Maybe not this sharp of a curve, but that's what we're looking for. So when I'm trying to create a function, the first thing that I want to notice about my function is where is the asymptote of my function. Now remember, the asymptote, that funny word we talked about, asymptote. The asymptote represents that line that our function gets super close to, but never actually touches. Now, most of the time, our asymptote is going to be 0. Our function is going to get super close to 0, but never touch. But if we look, our function is actually getting really close to this line, y equals -4. And that's our asymptote. That's our line that our function is getting super close to. So we're going to getting closer and closer and closer and closer and closer towards it as our function gets smaller and smaller and smaller as we go towards those negatives. Now, the asymptote is always represented by the number at the end of our function. So the asymptote is always represented by this term right here, whatever we're subtracting at the end, because typically our asymptote should be at 0. And so typically we're subtracting 0 from the end of our function. If we look at all of our previous equations, we didn't have a number at the end of it. So we're subtracting 0. So the asymptote for all of these functions here that we looked at earlier were all 0 because they didn't have anything subtracting. But because this one, we want our asymptote to be -4, that means we have to subtract 4 from our function to shift it down 4 spaces. So everything about our function just got shifted down 4. So now that our function got shifted down 4, we need to figure out, okay, what rate and what y-intercept do we want? Well, our y-intercept, if we look, let me draw like a better, I don't like this, the curve that we have on this one. So we had our asymptote at y equals -4. And then let's draw this function like that. So let's pass like that. So if we look, our y-intercept on here is -1. But the thing is, that's my y-intercept after I've shifted down. After I've shifted everything down 4 spaces. So the actual y-intercept that's going to show up in my equation needs to be the y-intercept that was before it got shifted. So I can't put -1 in here because that's my shifted y-intercept. So what I have to do is I have to think, okay, what number do I shift down 4 from in order to get to -1? So I need to essentially go up 4 spaces. So 1, 2, 3, 4 is actually going to be 3. So my original y-intercept should have been 3 before I shift down 4. So I'm going to write 3 in for my y-intercept. And the last thing we need is our rate. Now, the rate isn't necessarily as important, but what we have to realize is that our rate needs to be an exponential growth. We need to have a growth for our rate. Now, remember, if b is greater than 1, then we know we are going to be increasing. If b is less than 1, we know we are going to be decreasing, decaying. If b is less than, gosh dang it. If b is less than -1, then we know we are decreasing very rapidly, going down towards the negative. So which of these patterns do we want? Well, we want the first one. So we just need a number that's greater than 1. So what's a number that's greater than 1? I don't know, 2. So we want our rate to be 2. So this could be an exponential function that works. 3 times 2 raised to the x minus 4. Now, this isn't the only option. There could be plenty other exponential functions that could pass through those two slalom points that we have here. But this is an easy one that we can work with. So y equals 3 times 2 to the x would work. All right, let's look at a word problem. So in the year 1990, the total number of metric tons of copper produced in the world was 495,000. Each year since the 1900s, the total number of metric tons of copper produced has increased on the average of about 3.25% over the amount produced the previous year, which function models the total number of metric tons of copper produced in the year that X years since 1990. So essentially, this is saying every year after 1990, so 1990 produced 49,000 or 495,000 metric tons of copper. Every year after that, they produced another they produced the same amount plus an additional 3.25%. So an additional 3.25%. It increased every single time. So if given a random year, could we figure out how much copper was produced using this rule? That's what we're looking for. So we know we need to think, okay, y equals a times b to the x. That's what we're working with, right? Well, a is our y-intercept. So what number do we start with in this problem? What was our addition or our starting amount? Well, we were told in our starting year of 1900, we had 495,000. So our A needs to be 495,000. So, okay, all of our answers have 495,000 as starting value. So we know that's not going to work. But if we look at these two, C and D, they don't match our thing because we know X needs to be the exponent. Well, the X in this case is our rate. So we know it's not going to be C. And we know it's not going to be D. So it's going to be one of these two. So that from there, we need to figure out, okay, what is our B? Well, once again, B is that rate. It's that growth or decay. Well, let's think. Is our rate, are we increasing in our amount or are we decreasing every year? So if we look, the produce has increased on an average of 3.25%. So we are increasing. So we are growing. So remember, growth occurs when B is greater than 1. Decay occurs when B is less than 1. So we want a growth, we need to be greater than 1. So we know we're going to start at 100%. So because they are always producing at least 495,000 metric tons of copper and then an additional 3.25%, we know we're starting with 100%, and then we are adding on an additional 3.25% every single year. So you're getting an additional 3.25% and then an additional 3.25% comparatively to the previous year. So let's figure out what this percent is. So if we add these two numbers together, we get 103.25%. So that is our rate. We're increasing by 103.25% every single year. Now, the thing is, this is a percentage. In order to turn our percentage into a rate, we need it to turn this percentage into an actual number or an actual decimal. So when turning your percentage into a decimal, we move our decimal place 2 places to the left. So this is 1.0325. This is going to be our rate. This, if we look, this number is greater than 1 by a little bit, just barely, but this is going to be our rate. So our is going to be 1.0325. So A is going to be our answer. Now, if we said if the amount of copper had decreased by 3.25% every year, if it had decreased, let's change that word. What we would have to do is we'd take 100% minus 3.25% if it's decreasing in amount every year. So we'd take 100% minus 3.25, which would give us whatever, they would give us 96.75. So 96.75 would then be our amount, and that would be our rate that we'd put in. So this would be an exponential decay if we're decreasing by 3.25%. So anytime it says you're increasing by a specific percent, take 100% and add that. If it says you're decreasing by a specific percent, take 100 and minus that. That's how you're going to get your rates for exponential growth and decay. So you're either adding to 100% or subtracting from 100%. All right. A group of cells grow in a number as described by the equation y equals 16 times 2 raised to the t, where t represents the number of days and y represents the number of cells. According to this formula, how many cells will there be in the group after the end of the first 5 days? So we have y equals 16 times 2 raised to the t. So y represents the number of cells at the end. So that's what we're looking for. What is y going to equal? Number of cells. And t represents the days. Well, in our problem, we're told what is the number of cells, so what is y, when t, the number of days, is 5 after the first 5 days. So all we need to do is just evaluate this function. We're going to do y equals 16 times 2 raised to the 5. We just plug in 5 for t, and then we're going to figure out what this function equals, which we can easily do this. So we know it's y equals 16 times 2 to the 5. Well, 2 to the 5, what is that? Well, that would be 2 times 2 times 2 times 2 times 2. You may need to use a calculator, or you might recognize that this is going to be 32. So we have y equals 16 times 32. I just realized on my notes I did 5 times 32, not 16 times 32, so I have the wrong number on my notes. Let me grab my calculator really quick, and then we can figure this out. Because all we have to do now is just multiply 16 times 32, and that's going to give us our final solution. So 16 times 32 is 512. So y equals 512. So even though we started with 16 cells, at the end of these first 5 days, we have 512 cells because we are doubling by 2 every time. Another thing you could have seen is, okay, I see my y-intercept is 16. I see my rate is 2. I could just do 16 times 2 times 2 times 2, and you could do that till you get to day number 5 to get 512. But the thing is, you need to realize that on day number 0, you have 16. On day number 1, you'd be multiplying by 2. On day number 3, so day number 16 isn't day number, or 16 isn't from day number 1. That would be day number 0. So that's the only thing you have to watch out for if you do it that way. But that's where we're going to stop our exponential functions for now. You're going to have a little Desmos activity and then some practice over this. And then lastly, an exit slip to finish out your day. So let me know if you have any questions. Yeah, and that's where we'll stop it.